Okay, now let's start discussing about another machine learning algorithm, which is the decision trees. Decision trees are versatile machine learning algorithms that can perform both classification and regression tasks, and sometimes even multi-output tasks. They are very powerful algorithms capable of fitting complex data sets. And decision trees are also the fundamental component of random forests, which are among the most powerful machine learning algorithms available today. But this is not what we're going to discuss now. Later in the course, we're going to talk about random forests. But for now, I'm going to discuss about how to train, visualize, and make predictions with decision trees. Like previously, we have a collection of labeled examples, and labels belong to the set 0 and 1. And what we want to do is to build a decision tree that would allow us to predict the class of a given feature vector. So for now, we're talking about classification. Of course, we have decision tree regressors as well. And there are various formulations of the decision tree learning algorithms, and we could consider one which is ID3 uh, now. The optimization criterion in this case is the average likelihood, and this is the formula we have. Uh, Basically, yi is uh, this is the average likelihood criteria that we want uh, to calculate or evaluate. As you see, it looks a bit like a logistic regression. However, contrary to the logistic regression, uh, which builds a parametric model FWB by finding an optimal solution to the optimization criteria, ID3 algorithm optimizes approximately by constructing a non-parametric model f fid3 of x equal to the probability of x considering y equals to y to 1. This is an illustration of a decision tree building algorithm, and the set contains 12 labeled examples. And as you see in the beginning, everything is here. You see these are our labeled examples. Let me see if I can turn this laser pointer on. Yeah, we have our 1, 2, 3, 2, 12 examples. Xi is the feature vector, and yi is the output value. This is the class that we are interested in. In the beginning, we only have one start node. This large thing is our node, and uh, it makes the same prediction for any input given. This decision tree, what it does for us is a split based on a criterion. The feature is basically if feature 3 x3 is smaller than 18.3. If it is yes, it comes to this node, and you see these are these values of our dataset x1, the example 1, example 2, 4, 6, 7, 8, 9. Their third feature is less than 18.3, and the other ones is more or equal to 18.3. So it basically branches in two different nodes. And then we have the prediction is made in one of the two leaf nodes. And because in ID3 the decision to split the dataset on each iteration is local, it doesn't depend on the future splits, the algorithm doesn't really guarantee an optimal solution. The model can be a tree at the cost of possibly taking longer to build a model. And the most widely used formulation of a decision tree learning algorithm is C45. It has several additional features as compared to ID3. For example, it accepts both continuous and discrete features. It also handles incomplete examples pretty well. and it at the same time solves the fitting problem by using a bottom-up technique known as pruning. And pruning consists of going back through the tree once it's been created and removing the branches that do not contribute significantly enough to the error reduction by replacing them with a leaf node. So this is a more sophisticated decision tree approach than the ID3. But there are more than that. There's another one, CART, for example, and scalearn use, for example, CART. There are so many different ones of them. But for now, let's see how we do modeling with decision trees in. For decision trees, I'm going to use again the iris dataset, and I'm going to load it this time not from a locally saved file but from a scalearn dataset. And then I'm going to define I'm only using petal lengths and widths as the feature vector for the features to make the prediction, and then I put y as the iris target. And again, as easy as the previous models that we have already built, I'm going to initialize the decision tree classifiers because I'm going to predict the classes, and I'm going to put the limitation of the maximum depth to be 2. You can play with this and put different values, and I'm going to talk a bit further after this example about the other restrictions that you could put and why we need to do that. And again, we are going just to fit the model, and this is done. And then I'm going to basically visualize the tree that I built. I'm saving it in a file iris tree dot, and then I'm going to show you again how does it look, but just let me do this first. Okay, this is the decision tree we obtained from the training on our dataset, and now let me tell you how we could make predictions based on this tree. For example, we are given a new iris flower and we want to classify it. We want to see what type of iris it is. So the first question we're going to ask ourselves is that whether the petal widths, as you can see here, this is we are always starting from the root, which is this node here. The question we're asking is whether the petal width is smaller or equal to 0.8, and if it was, we come here and then we predict that the class is a setosa. If not, we are going to right side and then we answer another question. If the petal width is less or smaller or equal to 1.75, and if it was yes, we conclude that it's a versicolor. If not, we decide that it's a virginica. But the decision tree is useful in giving other type of information as well. For example, it can tell us the sample basically can tell us how many training instances it applies to. It also can tell us a node's value attribute, the one that you see here, 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 and here. It can tell us how many training instances each class this node applies to. For example, these are all 50 values are setosa. Here, half. It could be versicolor or it could be virginica, that is why it's branching. Here it's versicolor 49 and 5 for virginica, and here 1 versicolor and 45 virginica. Finally, a node's Gini attribute measures its impurity, and the node is pure Gini equal to 0, as you see here. If all training instances it applies to belong to the same class, as you see here, it's quite pure, it's 0. But we have two different measures that we want to know which one is better to use, Gini impurity or entropy. By default, the Gini impurity measure is used when we are working with decision trees, but you can also select the entropy impurity measure instead by setting the criterion hyperparameter to entropy. The concept of entropy originated in thermodynamics as a measure of molecular disorders. Entropy approaches zero when moleculars are still unwell ordered. It later spread to a wide variety of domains where, I don't know, for example, it measures the average information content of a message. Entropy is zero when all messages are identical. In machine learning, it is frequently used as an impurity measure, as sets entropy is zero when it counts instances of only one class. So I go back to the question that we had at the beginning. So should we use Gini impurity or entropy? And the truth is, most of the time it doesn't really make a big difference. They lead to similar trees. Gini impurity is slightly faster to compute, so it's a good default. However, when they differ, Gini impurity tends to isolate the most frequent class in its own branch of the tree, while entropy tends to produce a slightly more balanced trees. So it really depends on you and the need of your project. As you can see, decision trees are fairly intuitive and their decisions are easy to interpret. And we often call those models white box model. In contrast, as you'll see, for example, random forests or neural networks are generally considered black box models. They make great predictions, these black box models, and you can easily check the calculation that they perform to make the prediction. Nevertheless, it's usually hard to explain in simple terms why the predictions were made. For example, if a neural network says that a particular person appears in a picture, it's hard to know what actually contributed to this prediction. Did the model recognize the person's eyes, her mouth, nose, whatever? On the other hand, the white box models, like decision trees, provide nice and simple classification rules that can even be applied manually if need be. Uh, Another thing about decision trees is that decision trees make very few assumptions about the training data, as opposed to linear models that if you remember, we had some assumptions to make. If left unconstrained, the tree structure will adapt itself to the training data, fitting it very closely and most likely overfitting it. So this is one of the bottlenecks and problems we have with decision trees. Such a model is often called a non-parametric model, not because it doesn't have any parameters, it often has a lot, but because the number of parameters is not determined prior to training, so the model structure is free to stick closely to the data. In contrast, a parametric model, such as a linear model, has a predetermined number of parameters, so its degree of freedom is limited, and that reduces the risk of overfitting, but at the same time, it increases the risk of underfitting, and this is also something that we're going to discuss later. So when it comes to the decision trees, to avoid overfitting the training data, we need to restrict the decision tree freedom during the training. And this is what we call regularization. Regularization is used to reduce the risk of overfitting. And the regularization hyperparameters depend on the algorithm used, but generally you can at least restrict the maximum depths of decision tree, for example. Uh, we can also use other few parameters that simply similarly restrict the shape of decision tree. For example, the minimum number of samples in a node before the node must have before a split, or the minimum number of samples a leaf node must have, or the fraction of total number of weighted instances, or maximum number of leaf nodes, or maximum number of features that are evaluated for splitting each node. So these are all could be used to somewhat restrict the shape of the tree so we avoid the overfitting problem. One other thing that I wanted to mention is also that, as I said, decision trees could be used both as classifiers and as regressors. And here you see a decision tree regressor And as you see, it's very similar to the classification tree that we built earlier. And the main difference is that instead of predicting the class in each node, it predicts a value. For example, suppose you want to make a prediction for a new instance xi equal 0.6, and then you traverse the tree starting from the root, and you eventually reach the leaf node that predicts a value. Oh, the predicted value, and this prediction is simply the average target value of the 110 training instances here. uh, it's the average of 110 training instances. uh, so at the end, uh, they are quite similar to each other. So decision trees are simple to understand and interpret. They are easy to use, they are versatile and powerful. However, they do have a few limitations. First, as you have noticed, decision trees love orthogonal decision boundaries, which makes them sensitive to training set rotations. This is what you're seeing in this figure. Uh, this figure shows a simple linearly separable dataset. On the left, as you can see, the decision tree can split easily without any problem. While on the right, after the dataset is rotated by 45 degrees, the decision boundary looks unnecessarily convoluted. And although both decision trees fit the training set perfectly, it is very likely that the model on the right will not generalize. And one way to limit this problem is to use PCA that often results in that is principal component analysis, which often results in a better orientation of the model. More generally, the main issue with the decision trees is that they are very sensitive to small variations in the training dataset. For example, if you just remove the widest iris versicolor from the iris training dataset and train a new decision tree, you might get the model differently, as you can see here. Uh, Actually, since a training algorithm is a stochastic, you could also get very different models on the same training dataset. So to limit this problem, normally random forests are used, and they are limit this instability by averaging predictions over many trees. And as I mentioned today many times, random forests are very powerful tools, and we are going to see them in the future lectures. That is that much as I had to tell you about decision trees. Next, we are going to talk about support vector machines.